Okay, Module 9. So far we have looked at single variables such as the mean and then the population and the proportion. These are the things we focused on. But there are other instances where we want to know the relationship between two variables. So the concept is sometimes called a bivariate relationships. So one of those things is a correlation. It exists between two variables. Somehow they're related to each other. Somehow they're associated with each other. So it is an association between two variables. And for at least for this class, there are three types: the positive one, negative one, and non-correlation. And it's easier to see what I mean by looking at the picture. So let's take a look at each. So the positive correlation typically goes from bottom left to upper right corner. It's positive correlation because in the algebra it's defined if you draw a line in there, the best fit line, it will go from bottom left to upper right, and that's defined to be a positive line. So this is positive correlation. For the negative correlation, it's the opposite. If it goes from upper left corner to bottom right corner, then it's typically negative correlation. And if it's just all random, then it we consider it to be no correlation. So the correlation will be 0. So how do you calculate the correlation? Oh, one more thing. If it's a nonlinear correlation, if it's a curve. So we are only going to consider linear correlation where it's a straight line. So calculating correlation, actually we're calculating what we call the linear correlation coefficient, and we use the R to signify that. It's the quantity of the measure of correlation between two variables. So to calculate the R, the correlation coefficient, you need the following values. So n, the number of pairs of sample data, this sigma sign, or this big E looking thing, it's Greek letter S capitalized. It signifies summation. So sigma of x will be all of x added together. Sigma of x squared will be sum of all squared x values. And if we put them in the parentheses, these are all all the x values, and they're squared. And then sigma of x, y, that means sum of x multiplied by y, all of these values. And R stands for, again, the correlation coefficient for sample data. And the formula for that is this. As you can see, it's pretty cumbersome to do by hand. So what we're going to do is use Excel, and it has a built-in correlation function, CORREL. So that's what we'll use. It is more important for you to understand what the R represents. So let's take a look at what the R says. So the R is always going to be between -1 and then 1. So it ranges from -1 to a +1. The order of x and y don't really matter, so it doesn't really matter which one you signify as x, which one you signify as y. The R is the measurement of a strength of a linear relationship. So -1 means perfectly negatively correlated. And then +1, if the R is actually a 1, that means perfectly correlated in a positive direction. And you should know that the R is vulnerable to outliers. So to calculate the R, let's take a look at the spreadsheet and see how it's calculated. So, given the data below, find the correlation coefficient first, and then determine if the correlation coefficient is significant using alpha of 0.05. So here's the data of sedan types. Then I want to know the correlation between the weight and the break-in distance. So I collected the data for all these car types. So here I calculate the correlation coefficient. So the function is, again, CORREL. What you do is type in CORREL parentheses and then select the weights, all these things, comma, and then select all the break-in distances. It really doesn't matter which way you do first, but I just did it in order of alphabet. So B here, C here. Plug it in, press enter. You get -0.087. Now I want to know if this correlation coefficient is significant or not. To do so, you need to look at the critical values of R, which is listed in this tab right here. Before we do that, we need to know how many cars we looked at. So if you do the counting, you see there's 32 cars. Okay, so let's go to the critical value of R tab. So here's a value of significance at 0.05 and 0.01. Since we're looking at the alpha of 0.05, we'll look at this column. For n, we use the closest approximation. So for 32, the closest number to that is 30. So look down to 30, and then we're looking at column B. So the intersection between the two is 0.361. So for this value, we're going to use 0.361. So let's go back to this tab. So the critical value for R when n is 32 is 0.361. We use the critical value for R when n is 30. This is how you do the comparison. So we convert this negative correlation coefficient to a positive number for comparison purposes. So we compare 0.0867 to 0.361. Here's the rule. So since the correlation coefficient is smaller, the positive number of this is smaller than this, we can conclude that there's not sufficient evidence to support the correlation between the weight of the car and the braking distance. So what that means is that it looks like based on this data, there's really no correlation between the weight of the car and then the braking distance. So it seems to mean that the heavier the weight, it doesn't necessarily mean the braking distance is greater. So that's how you can use correlation coefficient calculation between two variables. So that's the first part of this module. The second part of this module is, before I go ahead, there's a common error. It says that the correlation implies causality. It doesn't mean that. So for example, say we determine that there's a correlation between the gas price and miles driven by consumers. It does not imply that the increase in gas prices causes people to drive more or less miles. So even if there's a correlation, that doesn't mean it causes something else to happen. So you should keep that in mind. So now moving on to simple linear regression. Basically, regression comes down to how we can predict the value of one variable given the other value. So we use regression to predict future values, for example. And we're going to focus on the linear regression and moreover simple linear regression. So what it does to you is that the regression relationship is going to be linear, a straight line. And then we'll use the procedure called the simple linear regression. So the regression is a straight line, so which has a regression equation of this. Y hat is equal to B0 plus B1 times X. And then Y hat is the response or the calculated value. B0 is the y-intercept. The B1 is the slope. And then X is the explanatory or the independent variable. Regression, to do regression by hand, it's very, very long and cumbersome again. So we're going to use Excel to figure out regression equation. And to do so, we'll use the function called the linest, L-I-N-E-S. It's short for linear estimate. And so let's go to spreadsheet to see how we can use this linest function. So say a company company executive wants to predict how far a piece of machinery moves given the hours as an input. The data is shown below, and then we want to predict the amount of the distance if the hours were 30 hours. Okay. So for this class, here's the table of regression data. And if you want to know how to do this, you use linest function. It's an array function. So if you're curious how this table is created, you should look up the linest function and how to do array functions. You don't need to know how to do that. For this class, this table is be given to you. What you have to do is be able to read this table and then answer the question like this one up here. So for linear regression, you have to be able to do two things. One is to get the linear regression equation. That's the first part. And then second is use the equations to do the prediction. So let's do both in this equation, or in this example. So if you take a look at this, you see these labels here: coefficient B1, intercept coefficient B0, standard error, all these things. And then the correlation down here, calculated using the CORREL function. So how do you know what the regression equation is? Well, if you remember, the equation is y hat is equal to b0 plus b1 times x. So this b0 corresponds to b0 up here, and the b1 corresponds to b1 up here. So you already have the b0 value and the b1 value. So basically, you just plug and chug. So if I use these values to rewrite the regression equation, it will look like this. Y hat is equal to 17.76x plus 111.36. I'm just rounding at 2 decimal points, but the actual values are here. Okay, so that's how you get the equation. You already have the template. All you have to do is figure out what B0 is and B1 is and plug it in. So if the question asks for a regression equation, that's all you have to do. For the second part, you have to predict the amount move if the hours are 30. So let's use a regression equation to figure out the amount move if the hours are 30. So the 30 will be the value of x. So what we do is plug that into x here. Manually calculating 17.76 times 30 plus 111.36 will give you 644.16. So that means we predict that given 30 hours, the machine will move approximately 644 feet. So that's how you do the prediction. You first get the equation, which is here, and then figure out what the x is, which will be given to you in the problem. Plug it into the regression equation, and then do the calculation. And you get the prediction right here. So that's the extent of how far you have to do the regression analysis. Regression analysis, there's a lot more to this, but for this class, that's as far as we will cover. So that's how you do questions about correlation coefficient and regression equation in this module.